In our final video discussing the IP protocol, we're going to take a look at IP version 6. The initial motivation to go to a new version of IP was the potential exhaustion of IP addresses. When the Internet was first conceived, the 4.3 billion possible IP version 4 addresses were considered sufficient for all possible hosts. However, in the early 1990s, the rapid growth of the Internet predicted that the IP version 4 address space would be exhausted in the future. Note that by April of 2017, the regional Internet registries had run out of medium-sized address blocks that could be allocated. So, the Internet Engineering Task Force, IETF, set out to revise the IP protocol, expanding the IP address space from the IP version 4 32-bit length to 128 bits. This provided unlimited address space. In fact, we could assign an IP version 6 address to every atom on the surface of the Earth and still have enough addresses left over to do another 100+ Earths. Since the IP protocol needed to be upgraded, the IETF set other goals to improve the performance over IP version 4. Some of these were to speed the processing and forwarding, to facilitate the quality of service, to add built-in security, and provide better support for multicast. IPv6 supports auto-reconfiguration and renumbering of addresses, in contrast to the manual and DHCP renumbering of IP version 4. IPsec, with its capability of encryption and authentication, is built into IPv6 instead of an add-on. With IPv6, end-to-end connection integrity is achievable, something that is not within the capability of IP version 4. The IPv6 header has a fixed length of 40 bytes instead of a variable length. Also, packets are not fragmented en route. Let's look at the IPv6 packet format. The packet is simplified over the IPv4 packet. This new version packet has fewer fields than the IPv4 version. The first field is the IP version number. And the next two fields are the priority and flow label. The priority field is also called the traffic class field. It provides much of the same functionality as the IP version 4 type of service field, classifying traffic for management and support of quality of service, as well as providing congestion control. The flow label field is new to IP version 6 and enables the ability to track specific traffic flows at the network layer. A flow is a sequence of packets sent from a particular source to a particular destination, for which the source desires special handling by the intervening routers. The payload length is the same as the IPv4 length field, and this field includes the length of the data portion of the IP version 6 packet. The next header field is the same as the IPv4 header field. The hop limit field is the same as the TTL field in IPv4. It has been renamed to more correctly describe the way that this information is used, counting router hops instead of time to limit the lifetime of a packet. There is also no option fields. Instead, the option functionality is implemented by extension headers in the data field. The data field of the IPv6 packet contains the application payload data plus the upper layer headers plus the extension headers just mentioned. Most of the packet length, 32 bytes, is taken up by the increased size of the address fields. Because the length of the address field are so large, the IPv6 address notation is different. An IPv6 address is represented as 8 groups of 4 hexadecimal digits, each group representing 16 bits for a total of 128 bits. For more information on the IPv6 addressing, check out the additional links in this week's iLearn section. The checksum has been eliminated because it does not provide enough error protection to warrant its performance impact. The transport and link layers already provide sufficient error protection. Fragmentation is no longer handled by the routers. Fragmentation must be handled by the source host. For this to work, the source host must determine the smallest MTU on its packet's route to the destination host. In other words, the source host must be able to determine if its packet is too big along the entire route from source to destination. To enable this capability, IPv6 incorporates a new version of ICMP. As the world is transitioning to IPv6, the Internet now has a mix of IPv6 and IPv4 routers and hosts. How can the network operate in this transition environment? In this mode, IPv6 packets are tunneled inside the IPv4 packets. This is essentially another encapsulation, much like the upper layer protocols are encapsulated by a lower layer protocol. This next slide shows a logical and a physical view of the tunneling. In this case, a router A is sending an IPv6 packet to router F. Router B receives this packet and encapsulates it within an IPv4 packet and sends it to router C, which forwards the IPv4 packet to router E, going through router D. Router E de-encapsulates the IPv6 packet and sends it to router F. Note that routers B and E must be running a dual stack, that is, both IPv4 and IPv6. IPv6 adoption has been slow. The IPv6 RFC was published in 1998. The main reason for the snail's pace is monetary. It takes a long time and is expensive to change out the infrastructure, all the routers, operating systems, and other auxiliary equipment. So 20 years on, where are we? As of this edition of your textbook, 2016, only 8% of the Google clients were using IPv6. Only 1/3 of the U.S. government domains were IPv6 capable, even though there have been mandates to transition since 2008. There has been progress since 2016, but it's still slow. Interestingly, in 2019, half of all the IPv6 users on the planet are in India. In our next video, we'll close out Chapter 4 in the network layer with a high-level discussion of software-defined networks.